The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading, interdisciplinary solutions to address significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. PAIR research areas include advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation. Look into the factors and mechanisms influencing human health and wellness and develop evidence-based solutions. And generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good afternoon, ladies and gentlemen, colleagues and students. Welcome to this PAIR Distinguished Lecture. As you know, PAIR holds these distinguished lectures and seminars from time to time. And this is a very important platform for us to communicate between the PolyU researchers and external researchers. And today, we are very happy to have Professor Chu from Tsinghua University to give the seminar. And before let's start, I would like to invite Professor Zhang Kai-Wan, the Associate Vice President and the Dean of Graduate School, to introduce our speaker. Professor Wang, please.
Hello. Okay. Ladies and gentlemen, it's my great pleasure to introduce today's seminar speaker, Professor Chu Xiaobo, the Changjiang Chair Professor in the School of Vehicle and Mobility in Tsinghua University. Professor Chu is a leading expert in intelligent transportation systems, vertical transportation systems, and emerging mobility service. His research focuses on integrating vehicle, infrastructure, cloud technology, and low-altitude transportation to build smarter and more connected mobility networks. At Tsinghua University, Professor Chu leads the Emerging Transportation Solutions Research Group and holds key leadership positions in several national laboratory and innovation centers dedicated to low-altitude transportation and intelligent mobility. Professor Chu's work supports China's vision of new quality productivity forces and urban sustainability through cleaner, smarter, and more efficient transportation solutions. His research helped tackle challenges such as energy consumption and carbon emissions. Ladies and gentlemen, please allow me to highlight two examples of Professor Chu's teamwork. First, as transportation moved to the era of 3D mobility, Professor Chu's team, together with industry partners, developed the world's first electrical modular flying car with compound wing, 全球首款复合材料机翼电动模块化飞行汽车 quite long. This vehicle offers an exciting vision of future point-to-point car travel, air travel, and perhaps one day, instead of booking an Uber, we can simply book an air taxi. Second, Professor Chu's team developed an award-winning demand-responsive bus dispatching platform. I think in Chinese it's 响应式需求公交调度平台. The system uses real-time data to match service with passenger demand and has been successfully deployed in Zhuzhou City in Hunan Province. Professor Chu is a member of Academia Europaea, or the Academy of Europe, and a fellow at Europaea. His visionary research helped turn forward-looking mobility concepts into practical solutions, building intelligent, sustainable, and people-centered transport system that will define tomorrow's cities. Without further ado, ladies and gentlemen, please join me in welcoming Professor Chu to give us a talk.
Thank you, Professor Wang, for a very nice, but a very lengthy introduction on me. Very good afternoon, everyone. It is such a great honor to be invited to visit PolyU again after quite some years. My first public seminar with PolyU was held in 2018 when I was about to join Chalmers University of Technology in Sweden. At that time, Professor Wang, Shuan Wang, is one of my closest collaborators throughout the past 20 years. My second time of delivering a public seminar in PolyU in 2022, when I relocated back from Sweden to Beijing to join Tsinghua University to establish the emerging transportation group in Tsinghua University. During the second seminar, I introduced a few plans that we are going to work on. And this is my third time to deliver a public seminar in PolyU. And today, basically, what I'm going to do is to introduce what we have done in the past 4 years from 2022 until now in the area of emerging transport. I will share my thought with future transport, including autonomous driving, including cloud control, as well as transport verticalization, the low altitude verticalization, that's flying vehicles. First of all, I would like to take this opportunity to advise a little bit about my institution. I'm from School of Vehicle and Mobility, Tsinghua University. Our school is a relatively new school. It was rebranded in 2019 from the former Department of Automotive Engineering by introducing the new component of transportation and mobility. At the moment, we have over 70 academic staff in our school and annual research income of 500 million Chinese yuan per year, dealing with the most pressing, challenging topics in the area of vehicle and transportation, electrification, automation, connectivity, shared mobility, as well as most recently, transport low altitude verticalization. We host the State Key Laboratory of Intelligent Green Vehicle and Mobility. For this lab, in the past 30 years, we oversaw the progression of Chinese vehicle electrification and automation. And as requested by the Ministry of Science and Technology, Ministry of Transport, since 2022, our lab is in the development and regulations of low altitude transport verticalization. Our school also hosts 3 top-tier international journals. The first one is in the area of transportation electrification. The title is E-Transportation, edited by academician Professor Ouyang Minggao, ranking number 2 in the category of transportation science and technology in this year. The second one is Journal of Intelligent and Connected Vehicles, edited by academician Professor Keqiang Li, in the area of vehicle connectivity, vehicle automation. The third one actually was established by myself and Professor Shuai Wang together. We are both the foundational editor-in-chief, founding editor-in-chief, and the name is Communications in Transportation Research. So in the past 3 years, we ranked number 1 in the category of transportation by Web of Science. Later, I will introduce a little bit about the journal, and you are the most welcome to submit work to our journal. Okay, back this little bit about my team. The theme of my team is System Physical AI for Transport Autonomy. A few representative works. The first one, as mentioned by Professor Zhang Wang just now, we developed these flying vehicles in collaboration with Cherry Group and Aerospace Group. This is vertical takeoff and landing aircraft, but energy consumption during the cruise stage is very low. It's comparable to a surface vehicle. The energy consumption for 1 kilowatt-hour can fly for 5 to 6 kilometers. That's comparable with our surface vehicle. We also develop a physical AI digital twin system to accelerate the testing and design process of all different types of new vehicles, including the surface vehicles and flying vehicles. We also contribute a lot in the like vision language action model for autonomous driving of commercial vehicles and cloud control, which I will introduce a little bit later. Okay, this is the system physical AI for transport autonomy, or basically the theme of our research. There are 3 unique features. The number 1, we have 3 layers. It's cross layers. The bottom layer, we have the assembly level or parts level. We are working together very closely with our industry partners, for example, Pangood for the electric motor and NRB for the bearings, in order to make autonomous driving possible, make the action, the vision language action, the action possible, to deal with the second problem, the virtual real-time alignment problem. This is the second feature. The third feature is we use a lot of AI tools to generate and also select, not only as a generator, but also as a selector for different scenarios during the autonomous flying and the autonomous driving process, as well as the intelligent machinery, embodied intelligence. As long as we have multiple different types of vehicles working together, that's for swarm intelligence. That's in the system level. So we have 3 levels: the parts level or assembly level, and contribute to the vehicle level for autonomous driving and autonomous flying. and that's a single vehicle level. If we have multiple vehicles working together, that's swarm intelligence, that's the system level. This is the logic for the research group, the theme of logic or research group. Back to today's topic, I will start with a more general picture regarding the most fundamental problem of urban mobility system. The most fundamental problem is the asymmetry or imbalance between the demand and supply. Because demand is changing all the time. We have morning peak hour, a lot of traffic. We have afternoon peak hour. We have low demand period during night. But supply will be provided by infrastructure plus a combination of infrastructure, cloud, and the vehicles. So during the morning peak, a lot of traffic. If we want to accommodate those traffic, if cloud computing is not enough, we can allocate more resources. We can allocate more computing resources during the morning peak. That's not a problem. If we are lack of vehicles, we can allocate more vehicles because a lot of vehicles are currently parking in the car parks. But for the infrastructure, it's rigid. There is nothing we can do. During the morning peak, we need 5 traffic lanes to accommodate the traffic, but not possible. If you have 2 traffic lanes, that's 2 traffic lanes. Not possible to be converted in real time to 5 traffic lanes. So accordingly, page 5 or page 6? Yeah. Accordingly, throughout the past 30 years, 40 years of intelligent transportation systems, what we are going to do is to minimize the role of infrastructure and enhance the role of cloud and vehicles. Over the past 20 years, 30 years of intelligent development of intelligent transportation systems, we always wish to minimize the role of infrastructure because infrastructure is rigid, and we want to enhance the role of vehicle and the cloud. So in the following, I will use a few examples of increase the role of cloud, increase the role of vehicles, or minimize the role of infrastructure in order to make our transport system better. So the most direct way is to promote public transport because for one public transport can accommodate 9 to 20 passengers. Accordingly, the burden to infrastructure is much lower in comparison to passenger vehicles. And then the carbon rate per passenger will be much lower in comparison to the passenger vehicles. But our current public transport system, we are suffering from a few drawbacks. Number one is a very long journey time because we need to stop at each and every station, even if nobody is alighting or nobody is boarding. And in order to cover a big range of area, we increase the nonlinear coefficient of bus route. The second issue is transfer. If we want to, according to our data in Beijing, 41% of trips need transfer to complete our journey. And for each transfer, it takes an average of 11 minutes because for the transfer, you need to stop and get off. You may change another platform, wait for the connecting buses, long and uncertain time. So accordingly, we need to improve the current practice in order to increase the market share. Basically, what we are doing for the first study is to develop a smart brain, the cloud system, in order to have the benefit of both traditional public transport and also the ride sourcing platform. Basically, our best hope is to have a travel time transportation mode that's with a travel time similar to a taxi, point to point travel time similar to a taxi, while its cost and the carbon rate and the burden to infrastructure is comparable to a traditional bus by using a smart cloud operational platform. So I will, for this audience, you are most of you guys are not from the area of vehicle engineering or transport engineering. So I will use three very illustrative examples to introduce our idea. Basically, the left-hand side, the base scenario is the current Uber pool system or Didi pool system. So you have one vehicle to pick up a few passengers at a different location. Accordingly, you need to stop for multiple times, and you have a long detour. You have high nonlinear coefficient. Something wrong with the system. Right? Keep moving all the time. No. Yeah. And what we are going to do is to introduce two schemes or two innovations. The first one is we wish to allow our passengers to walk no more than 300 meters. To walk for no more than 300 meters in order to reduce the nonlinear coefficient, to have the most direct route from origin to destination. Okay. The second idea is to we allocate floating stations to gather the passengers nearby in order to minimize the number of stops from 3 to 1, based on this example. There are three components of this demand responsive microtransit. The module one is a network design. So how many floating stations in a zone and the locationing, the best optimal locations of each floating station. Floating station, that means you can only board and alight at any of those floating stations. The second module is the smart brain, the dynamic routing and scheduling, optimizing the route of flexible route of vehicles, and also the combination between passengers and the vehicles. The third one is the optimal redeployment of number of vehicles from one zone to another zone. Two innovations I mentioned just now. The first one is vehicle customer coordination. So we allow the vehicle to walk a little bit to the floating station, and based on the optimal calculation, the optimization, we allocate the second one, the dynamic flexible routing for each and every journey. We use a lot of AI-driven tools with self-learning and self-improving capacity. So this is the traditional digital twin system or system AI system. We have the user end, we have vehicle end, we have smart brain server. For the user end, we submit the request or origin or destination or final destination or current location. And we have the driver end, we have optimal plan and the locationing information and the speed information and vehicle dynamic information to the cloud in order for the smart brain to calculate the best best possible route position and passenger route from their current location to the floating station. The logical architecture, we have interfaces between the user end and smart brain and the driver end. From smart brain, we develop the user app and the vehicle app. And we use a lot of AI tools to accelerate the calculation because this is a very complicated problem. We have a lot of pre-training in order to have calculations, the result in real time. We developed the algorithm in collaboration with Professor Wang. It's a large-scale online optimization problem. We reduced the computation time to only 5% in comparison to the commercial servers. At the end, every 10 seconds, we can update the plan, and every 1 second, we have the calculation result, which allow the real-time computation. And this is the optimal redeployment from one zone to another zone problem. Basically, the system has been deployed in Zhuzhou City, Hunan Province for the first place. It has been running for 18 months already. In the past 6 months, we collect the data to evaluate the performance. Basically, our demand responsive public transport system, the travel time is only 20%, 21% higher in comparison to a taxi from floating station to another floating station. Only 21% higher. That is comparable to to the taxi, to ride sourcing system. But the cost by using taxi is 9.16 Chinese yuan, and we only collect 2 Chinese yuan, it's only 20%. If you calculate the carbon the carbon, and if you calculate the burden to infrastructure, we are much lower. It's like 20% or even less. We are using the buses manufactured by CRRC, which is one of the largest vehicle manufacturer, bus van manufacturer in the world. We developed the user app, we developed the driver app, and we use Beidou for positioning purpose. And because we have strong benefit of cost, we have cost benefit or travel time is comparable accordingly, or we gain substantial amount of market from the taxi industry. According to our real data for this demonstration zone, the number of the DD and AMAP services has reduced to 40%. After launch of our system, and the annual revenue, the daily revenue has been increased for 12 times during the weekday, 24 times during the weekend, the highest day 36 times, which allow a positive business model for the public transport operators. And after that, we have been deployed in another 5 cities in China, and in the following year, in collaboration with King Dragon, Xiamen King Dragon bus manufacturer, and also CRRC, we are going to deploy another 20 cities. It was reported by CCTV and a few international news. This the several other places have been launched in the past 6 months. This is number 2, number 3, number 4, number 6, and number 5. Okay, for the first case study, basically what we are doing is to increase the role of cloud. So remember, for the mobility system, the supply will be provided by infrastructure, cloud, and vehicles. For the first case study, we increased the role of cloud in order to make our transportation system better. The second case study, we are going to use autonomous driving technologies to develop new types of vehicles. It's something in between passenger vehicles or a minibus and a train, in order to enjoy the benefit of both, to increase our capacity. The second example, we are developing a new new types of vehicles. So we have done a lot of works for the autonomous driving based on the scenario generation and end-to-end vision language action model. In that process, we develop a technology for the very precise control. We allow the vehicles can be connected and all disconnected while in motion, like what we have done for this vehicle, the first 3 ones. This is also a collaboration with CRRC. Basically, the vehicles can be connected while in motion, can be disconnected while in motion. Accordingly, if somebody wants to get off, If somebody wants to get off, you can transfer to the last cabin by using the autonomous driving technology to get rid of the last cabin. And the last cabin can use the demand responsive model as I introduced just now to distribute and collect new passengers. Accordingly, from one zone to another zone, you never need to stop. It's a train system. You never need to stop. Only if somebody arrive at the final destination, nearby the final destination, you transfer to the last cabin, and then you get rid of the last cabin by using the demand responsive technologies to distribute the passengers and collect new passengers. This is like what this diagram is showing. From origin to destination, only the first several kilometers and the last several kilometers, you have some stops. Anything in between, never stop. When you arrive at your final destination, you transfer all the alighting passengers to the last cabin by using autonomous driving technologies to get rid of the last cabin and use the demand responsive model to distribute those 1, 2, 3, 4, 5, 6 alighting passengers, and that's 8 boarding passengers. And you can use the demand responsive model to calculate the floating stations. So you only need to stop for 3 times. The first time, 3 passengers will get off, and 1 passenger board. And the second floating station, 2 passengers, 2 alighting passengers, 3 boarding passengers. The third floating station, 1 alighting passenger, 4 boarding passengers. As soon as you collect all those passengers, and then you can arrive at the main corridor and connect to the train system. So the second example is basically we develop a new types of vehicles for increasing the future infrastructure capacity. Accordingly, the role of vehicles will be enhanced. The relative role of infrastructure will be minimized. So the third example is basically the ultimate solution. The ultimate solution, as I introduced just now, we have urban mobility system. The supply will be provided by cloud, infrastructure, and vehicles. We want to minimize the role of infrastructure. So which types of transportation mode will have the lowest requirement for infrastructure? That's flying, right? Because for fly, it's a water route from one location to another location. We do not need to construct the physical infrastructure. We only need to have water infrastructure, water route. So accordingly, the urban area mobility leverages water air road network to reshape the resources allocation, overcoming the physical constraints of traditional infrastructure. However, the low altitude flying is not new. In 1939, we have helicopters already, but helicopters never became a mainstream choice for commuting purpose. At the moment in China, in such a large country, we only have 800 civilian-used helicopters. Why? Only 800. It's not an industry at all. Why? Because you only have 1 propeller, you only have 1 engine. So the reliability level need to be as high as 10 to the power minus 7, 10 to the power minus 8. You only have 1 propeller, you only have 1 engine. So the system reliability equals the parts reliability. Thanks to the recent development of electric vehicles. For the electrical vehicles, we have a distributed control. Take a look at our flying vehicle. For this example, we have 8 rotors, right? We have 8 rotors. For each rotor, we have 1 electronic motor, and they are running independently. So they are running independently, they are distributed control. Accordingly, even if one of them is not working, you see the second row, the third one is not working right now, right? I turn off the second row, the third one, we turn off. But still, we can maintain the stability and safe landing. Accordingly, the parts reliability, there is a big difference between the part reliability and the system reliability. So accordingly, if we can accommodate two malfunctions, that means the reliability level for the rotor for the electronic motor can be reduced from 10 to the power minus 7 to 10 to the power minus 3. That's vehicle level. That's a surface vehicle level. That's not the aircraft level. That's a surface vehicle level. If we can use the supply chain system of electrical vehicles, the cost will be much lower. It's only 5%. It's 5%, 1/20th of aircraft, of a helicopter. So because we have electrified distributed control, we can use the supply chain of vehicle industry. We can significantly reduce the cost to only 5% of helicopter. According to the estimation by BCG and Rolenberg, the flying vehicles, two-seater or three-seater flying vehicles, the cost will be reduced to $150,000 US, or according to all estimation, will be 500,000 to 1 million Chinese yuan per flying vehicle. If we are using supply chain of electrical vehicles and we are using assembly line instead of customized design. However, at the moment we have over 800 different configurations of flying vehicles in the world, and in the end, we may have only 5 or 6 that can be useful for our current market. And how to convert the 800 different configurations to 5 or 6? What kind of drone design or flying vehicle design have the potential to gain substantial amount of market from our surface commuting services? And this is what we have done in the past several years to analyze the scenario. This is a very large study to compare 10 largest metropolitan areas in the United States and 12 largest cities in China to have all the design parameters, the cruise speed, the lifting capacity, the total tonnage, the number of seats, all the other self-driving, the battery size, the battery type, all the different, the design parameter, overall design parameters of flying vehicles. This is some result for Beijing, Shanghai, Guangzhou, Shenzhen. We have the different configurations, multi-rotor, compound wing, tilt rotor, and the lifting capacity, the cruise speed, all the design parameters under different configurations, what are the optimal configuration. And we also conduct a study of Guangdong, Hong Kong, Macau, Bay Area. As we all know, we have 5 large airports in this small area. We have 13 large train stations in this small area, but the connectivity between different interchanges are not good enough. It is very rare for somebody to arrive at Shenzhen Airport and go to Nansha North for the connecting trains. If we can connect all those interchanges by using flying vehicles, by using different types of flying vehicles. If the distance is short, as I mentioned just now, you use the multi-rotor. And if the distance is 25 to 70 or 80, we use a compound wing. If the distance is long enough, like 100 between Guangdong and Shenzhen, we use the tilt rotor. And we can reduce the number, the travel time from roughly 2 hours to 15 minutes. If the travel time from one interchange to another interchange is 15 minutes, that's like different terminals in the same airport. So the connectivity will be much, much better. And it will certainly boost the economy. It is possible to integrate the vertical transportation system with the traditional hubs. This is the flying vehicle that we developed in collaboration with the Cherry Group and the Aerospace Group. It's a vertical takeoff and landing. And as I mentioned just now, during the cruise stage, energy consumption is very low. The energy consumption is only is comparable to the surface vehicle, comparable to a passenger car. And it's a modularized design. We have three components. We have component wing at the A. We have cockpit, intelligent cockpit at B. And we have the self-driving chassis at C. A plus B is the airplane. B plus C is the self-driving vehicle. And this is the operational mode. Is also demand responsive. The audio is not on, right? So I can introduce. So it's also a demand responsive model. Basically, you have a user app to order from your origin to your final location. And from your origin to the nearest vertiport, we use land transport, use the B plus C, the cockpit plus the chassis, self-driving from your home to vertiport. As soon as you arrive the vertiport nearby your home, you reverse into the compound wing, and then the self-driving chassis will leave. And now you have A plus B, that's an airplane, that's a flying vehicle. Fly from the vertiport to the vertiport nearby your workplace. And it takes a very short time, like several minutes from one vertiport to another vertiport, because the speed can be as high as 150 kilometers per hour. And then you send another chassis to pick up the cockpit for the final mile delivery from the second vertiport to your workplace. So this is the imagination for future. And for this product, we use a lot of digital twin or virtual physical testing process to minimize the risk for the physical experiments. And a lot of different tests, from summer to winter. And we developed it takes time. It's stuck. Many videos. And we develop a physical AI or digital twin system to accelerate the research and development process. And as I mentioned just now, from parts level to the vehicle level to the system level. And we use the UE and ASIM and Python to generate the environment. And we use a lot of AI tools to generate different scenarios, like different weather conditions, the snow condition, the heavy wind condition. And we also generate the non-cooperative target, like the drones, like the birds, some non-cooperative target. And we generate different wind conditions. This is another work at system level, the terminal management system or the vertiport system. As we can imagine, in future, in the vertiport, the takeoff and the landing, that will be the choke point for flying vehicles. That will have the highest density. Accordingly, we develop a safety management system for the terminals, and we consider the third-party risk on the ground, and we also consider the vertiport topology and operational rules, and so basically we simplify the current aviation process. That's a 5-stage, and to the only 2-stage in the terminal management of flying vehicles, in order to minimize to increase the capacity while maintain the safety benefit. This is the system that we developed for the terminal airspace management. It's like this is choke point. It's similar to traffic signal, the signalizing intersections. We developed a system with green and black, that's green signal, and the red signal in order to allow a vehicle to land and allow vehicle to take off or disallow the vehicle to land and take off. If in case we have some issues, we also developed the real-time conflict resolution protocols to minimize the risk. The system has been implemented in a general aviation airport of Chongqing City. The first one is a sandbox in our lab. The second one is a general aviation airport. We convert the general aviation airport in Chongqing to a flying vehicle validation or verification airport. So there are videos you can, the aircraft management, you can click the button. The other three as well. Yeah, for the multi-vehicles takeoff and coordination, for the takeoff and the landing test, and during the night environment, how to take off and landing, how to communicate between different vehicles. Okay, to summarize today's talk, and basically, I start with the most fundamental problem of transportation system, because our urban transport faces a core mismatch between dynamic changing supply, dynamic changing demand, and stable supply. It's a mismatch. In the past many years, we consider not possible to resolve. And we propose three solutions. The number one is to increase the role of cloud, to have a smart brain in order to better coordinate the vehicles. That's kind of swarm intelligence. And that's what we have done in the past many years for the intelligent transportation systems. The second solution is to develop new types of vehicles. For example, autonomous driving. Autonomous driving that allows the vehicles, the time distance between one vehicle to the successive vehicle only 1 second or even less. That increases the capacity. But for this example, what we are proposing is to have a physically connected platoons by using autonomous driving system to allow the vehicles to connect and disconnect via motion in order to minimize the number of stops or even reduce the number of stops to a very small number. But for the traditional bus, for each and every station, you need to stop. But for this system, you only need to stop 1 or 2 times during the first 2 kilometers and 1 or 2 times during the last 2 kilometers. Accordingly, we increase the capacity, we improve the level of service. And the ultimate solution for future is the flying vehicles, because the flying vehicles have the lightest infrastructure requirement, freeing transport from the ground infrastructure limit, and can have the potential to fundamentally resolve the supply-demand mismatch. That is the fundamental problem of urban transport. So at the end of my presentation, I would like to advertise my 2 journals. This is the journal that I mentioned just now, launched by Professor Shuai Wang and myself in 2021. At that time, we have been collaborating with Elsevier. And 2 years later, the journal was indexed by SCIE and SSCI with the highest impact factor in the category of transportation by Web of Science. I think our first impact factor is 12, right? The first one is 12, and the second one is 14.5, and third one for this year is 12.7. The reason we have reduction from 14.5 to 12.7 is change the platform, and we changed the for the first 4 years we collaborated with Elsevier, And since this year, we, we didn't renew the contract with Elsevier, and we go back to the Tsinghua University Press to publish with Tsinghua University Press, as requested by the Ministry of Science and Technology, and also this is our willing as well. At the moment, we have almost all the top tier university like MIT, Stanford, Cambridge, Oxford submit the journal to the article to our journal in the past, and we for the following, at least for the following 3 years, we still cover the APC. If your article is not overlength, if 10 or above, you need to pay the overlength charge. As requested by Elsevier, Professor Wang has stepped down last year to be the editor-in-chief for Transportation Research Part E only. And for me, I invited another editor-in-chief, co-editor-in-chief, Professor Xiaobo Li from, at the moment, in University of Wisconsin Medicine, but soon will join Northwestern University as a chair professor. The second journal is in the area of vehicle connectivity and automation. A journal of intelligent and connected vehicles, edited by the editor-in-chief Professor Keqiang Li and Professor Jianqiang Wang. I'm the executive editor-in-chief running this journal. The impact factor is 6.3, also rank Q1 journal. Yeah, you are the most welcome to submit your work to our journals and to support our, Chinese journals instead of international, journals. Okay, that's all I have to say. Thank you very much.
Okay, good afternoon, everyone. My name is Shuan Wang. I'm from the Faculty of Business. So now I will serve as a moderator for Professor Chu's seminar. Yeah. Okay. Yeah. So if anyone has a question, then please raise your hand, and you should first introduce yourself, your name, which department are you from. Also, we have a lot of people online, and I will also ask a few questions from those who attended Professor Chu's seminar online. So any question in this room? Yes, please.
Thank you very much, Professor, for your sharing. My question is a bit from the battery management systems perspective. In one of the slides, you mentioned about vertical takeoff points would possibly be sort of choke points later on as we move towards vertical mobility. So when it comes to battery management systems, where do you see it to be concentrated towards, say, for example, a parallel comparison will be like fuel pumps, gas stations in today's world. In future, it will be like battery power pack warehouses. Will it be concentrated at one place, or will it be spread out across any given region? Thank you.
Okay. Thank you for your question. Actually, this is a very important topic for the flying vehicles. I'm not working on battery management system, so I'm working on like autonomous flying, the vision, language action model. But according to my probably my colleague Professor Ouyang Mingo can better answer your question. And according to my judgment, battery is not the biggest problem for flying vehicles deployment, because if you want to deploy a flying vehicle in city area, the distance is very short. Even from Tsinghua campus to Yizhuang to another corner of city of Tsinghua of Beijing is only 35 kilometers. So if the distance is short, the energy density of batteries is not the biggest problem. But for the takeoff, you need to have a few special requirements for the battery itself. I think that's more important issue to talk about. Yeah. No worries.
Yeah. Any more questions? Then maybe I ask a question from online. So one question is, how many trials about using the flying vehicles have been conducted both in China as well as abroad?
Trials with passenger or without passenger?
I think it's with passengers.
With passenger at the moment, according to my knowledge, only Yihang, EHANG, and Xpeng, they have a lot of test flights with passengers. But for my flying vehicles, we never did that. We never did that. We have been flying for, I think, roughly around 1,400 kilometers already, all empty, with no passenger inside.
So a following up question from the audience online is, what are the key challenges for the flying vehicles?
Yeah, as there are a few challenges. Number one is you are using a lot of vehicle level reliability supply chain parts. Accordingly, you have a lot of malfunctions from time to time. So you need to accommodate, you need to develop very robust redundancy, safety redundancy plan in order to deal with different kind of malfunctions. That's the vehicle itself. The second one is it's very different from the civil aviation, so civil aircraft flying in the high air. In the low altitude, there are a lot of obstacles, non-cooperative objects like drones, like birds, like different target. So you need to have very good crash avoidance capabilities. So we need to borrow a lot of technologies from autonomous driving to identify the object, like identify the non-cooperative target, and turn to make some actions. The third one is in future, the density will be much higher in comparison to aviation, because aviation at the moment we only have 500 aircraft, aviation aircraft in China. Only 5,000. Only 5,000. But how many surface vehicles do we have? Surface vehicles, we have 500 million. 500 million. So in future, the flying vehicles, according to our estimation, will be at the magnitude of 10 million unit. So they have some interactions, especially in the terminal, in the vertiport. So we need to design the regulations for the vertical management. So the single vehicle level, the vehicle environment problem, and multi-vehicle problem.
Okay, next question, Professor Qingye Chen, Director of Europaea.
Yeah, thank you very much for a very inspiring talk. For these low altitude vehicles, I learned that like in Shenzhen, they already use for the good delivery. Yeah?
Delivery.
And it's an amazing achievement. But I also think about if you have more vehicles in the future, then you have a very limited time and space for maneuver, and especially when you fly in very low altitude. For example, if you let's say a small antenna, for example, very tall antenna, but very small.
Yes.
And then you probably cannot identify, and that will be a big issue, because if the vehicle hit the antenna, then probably hit somebody on the ground, right?
Yes,
That's one thing. On the other hand, now the weather is not very stable, a lot of suddenly big gust of wind and,
Yes.
and so on.
Yes.
And then if you look at the fluid mechanics point of view, you get this big turbulence, and then the vehicle stability is also an issue. So how do you see that's a solution for such a type of problems?
Okay. These are very good questions. So for the question number one, the capacity of flying vehicle of all air will be, according to the estimation by us and Chinese Chinese aerospace group, is only 2 to 3%, maximum 5% of land transport. It's certainly not the scale, not at the scale of land transport, surface transport. So we can accommodate all air, we can accommodate 3% roughly of the flying vehicles. That's not a problem. For the second problem, that's what we are researching on. The vision, language, action, or different models in order to better identify the non-cooperative target or some target very difficult to identify in order to minimize the risk, as you mentioned just now. That's for the GAST. We also developed the digital twin system to accelerate the testing process. We have all the different types of GAST to generate in our simulation system, and we developed the flying dynamics, flying control algorithm in order to minimize the risk of crash.
Yeah, I mean, if you look at the autonomous driving, right, it's only two-dimensional, and then you already have a lot of data available, images, and so on, and then you can have a different type of radar or whatever, but it's still not very safe, right? We often heard from time to time there's a crash or whatever. So I think at least a three-dimensional aircraft will be even more challenging.
Yeah, but the distance between one aircraft with another aircraft can be as high as 150 meters. That's very different from the autonomous driving. Autonomous driving from one autonomous vehicles to another to the successful vehicles only 0.8 second. That's like less than 10 meters or 10 meters, around 10 meters. So that's a different scale, 150 meters and 10 meters. So we have reasonably enough redundancy between one aircraft with another aircraft.
But if you look at the commercial aircraft, right, which is flying very high,
yes,
and sometimes you may have even the middle
that's true.
elevation.
That's true. That's like a Japanese airline.
Yes,
a few days ago.
Right.
Yeah,
then you can think you have in the cities, you have buildings, bigger towers or whatever. Then it becomes
that's true. That's true. For the buildings and towers, they are stationary objects. That's easy to deal with. The moving, dynamic, and non-cooperative target, that's the difficult problem we need to solve.
Thank you.
No worries.
Any questions? Yes.
The Department of Construction Management and Intelligence. I'm currently doing public transit, the transfer quality, and the interactions with the street level environmental perception. I was particularly interested in your demand responsive micro transit system and the design of transit hubs. But I was wondering, when determining the locations of these transit hubs, apart from the mainstream focuses on, for example, the travel demand and the operational efficiency, what other factors do you take into account?
Yeah. When select the optimal locations of different floating stations, number one is, as you mentioned, you a lot of traffic information. Number two is city topology information. We also use a lot of transfer learning. For one zone to another zone, we use AI to identify the most important features on the different topology, different combination of topology and transport information. So it's a transfer learning AI process It's not like stationary. We have only 4 or 5 features that we need to select. It's based on the our model to optimal the number of features and which feature is the most important feature for the selection.
Okay, but I'm wondering, are there any factors to take into account from the passenger side?
At the moment, for the cold start, the first selection, the first time of selection, no. But after several months of running, we update. So that information will be considered based on the 3 months running data.
Okay, sorry, man, I have one more question.
Yeah, sure.
Actually, my PhD thesis is about the operation and the management of autonomous vehicles. And you mentioned Yihang. Actually, I visited base of Yihang in Guangzhou last year. And they currently have multiple uses scenarios of the vehicles, for example, in delivering human organs, in firefighting, and even in high-end commuting. But they are all perfect imagination. They have fancy vehicles presented in the base. But my question is, what do you think the key challenges for these multiple use scenarios in the future?
Actually, the multiple use that you mentioned just now, they are the very low ceiling use scenarios.
Yes.
The commuting, even with only 1%, that's a big number. But the like firefighting, like the delivery of organs, that's a very rare situation. That number is not very high. And for the delivery of organ, you do not need such a big Yihang 216. You need a small drone that will be more than adequate to deal with the organ delivery.
Okay, thank you.
No worries.
Yeah. Any more questions from the audience? Yes.
Thank you very much for the presentation. My name is Daisuke Yasumoto. I'm from Logistics Department of PolyU. And then I would like to ask quite a basic question. Like, as you presented on-demand vehicles, I'm wondering the relationship between the conventional mass transit, I mean stable supply, and on-demand vehicles, just you mentioned. So like, for example, like in the future, like will the conventional transit be replaced entirely by on-demand vehicles, or they coexist in the cities? So that's my question.
Yeah. In my judgment, they will coexist. For the long haul journey from one location to another location, the conventional bus have benefit. For a zone area like a 5 square kilometer to 10 square kilometers, for zone area, demand responsive will be much more efficient. So the shortcoming of a large bus or conventional bus is the number of stops. So if the number of stops is limited, or the number of stops to the next stop, the distance is long. So the conventional bus certainly have benefit.
Okay, thank you very much.
No worries.
Yes, please.
Hi, Professor Chu, and thank you for sharing. I'm Liani, and I'm from SFT, and I'm really curious about your solutions about the floating station and also the eVTOL. I found that it actually takes some effort from the consumers. For example, the passengers need to go to a station, and also they have to like transfer their 车厢 to the destination they want. So how to incorporate this kind of consumer's preference in your study?
Yeah, that's a good question, because for the comparison that I mentioned just now, like the 9.16 Chinese yuan to 2 Chinese yuan, and the travel time of 21%, only 10 to 21% higher. That's actually is not an apple-to-apple comparison, because if you want to take a taxi, you do not need to walk. But for all solutions, you need to walk no more than 300 meters. But in reality, walking for a short distance is good not only for health, but also, to consume your time, right? That's not a bad thing, but we need to work together with like a social scientists or psychologists to measure the pros and cons of these 300 meters or how to identify the 300 meters or 200 meters. Yeah, that's a good question because we are comparing from floating station to another floating station. So that's not exactly the same with the taxi scenario. The taxi scenario is from your current station to your final destination. You do not need to walk at the very beginning. You do not need to walk at the very end.
Yeah.
Okay, I'm Hao Qinwang from Department of Logistics and Maritime Studies. So I have one question. With the development of low altitude traveling, so maybe one day it becomes true and reliable in our daily life. Then at that moment, when we travel, when we refer to our map, so nowadays we can know from our map, we turn left, turn right, or go up or go down. And then if we can choose travel with low altitude methods, so at that time we will need 3D dimensional map. But nowadays, when we go to cities like Chongqing with complex altitude structures, we found that it's quite difficult to navigate. So if one day the low altitude method becomes true, then we need a 3D dimensional map. So what do you think the challenge behind this new map?
Okay, that's a very good question. Have you realized the A map, Gaode A map? They have 3D maps already. All the buildings and the height of the buildings is 3D map. And we have been collaborating because Gaode is a map is one of the partner institute for our Beijing Key Lab. For the Beijing Key Lab led by Tsinghua University and supported by EMAP as well as China Airspace Group. So now we are working together to develop the 3D map throughout the world, not only for China, but also for like United States or Europe. And you can check the EMAP. So we have quite a few cities ready already, like Egypt, Sao Paulo, not only the Chinese cities.
Okay,
Yeah.
thank you.
We have 3D maps already in many cities. Yeah.
Okay, thank you.
Yeah, next question. Okay, there is one more from the internet. It's about autonomous vehicles. So the question is, China has many cities, and different cities have roads of very different conditions. Some roads may be very narrow and also bumpy. So in this case, do the cities need to improve their road conditions for using autonomous vehicles or not? And if yes, how can we balance the cost of improving the roads?
According to my judgment, the reason why we developed the vision language action model is to have a brain to identify the current situation and make the judgment instantaneously, instead of like the rule-based models at many self-driving technologies that in the past they can only have the high precision, high resolution or high definition map and other supporting environment in order to make autonomous driving possible. So I think it's certainly not the way forward. As long as we have the conventional vehicle running in the street can be used for autonomous vehicles as well.
Okay, thank you. Any more questions? If no, I think the time is almost up. So the next agenda is let's invite Professor Qingye Chen, Director of Pair PolyU, to present a souvenir to Professor Xiaobo Qu.
Okay, to express our appreciation to your talk,
Yes.
we make this a special souvenir for you with your name and the title of your presentation.
Okay, thanks a lot.
Yeah. Okay, I would like to invite Professor Wang, another Professor Wang here, to take a photo together.
Thanks
Thank
a lot.
you.
Thanks a lot. Thanks a lot.
All right, and I also wanted to say thanks to all of you to be here, and for those who may ask questions, I'd like to express my special appreciation. And for those online, we will encourage you to attend the pair seminars and lectures in the future. So please keep yourself tuned for our future announcement. Thank you very much, and this seminar is adjourned. Thank you.